studying about electromagnetism. Before we start with the chapter of electromagnetism, let's just want to know that what are the use and why we want to study electromagnetism. Well, most of the times, whatever things we see around us are actually electromagnetic waves, right? So because of electromagnetic waves, we are able to see things. Another application can be like radio and TV signals. These are nothing but electromagnetic waves. Also radar signals. These are electromagnetic waves. Then one more example can be, suppose we want to find out the speed of aircrafts and all. So that is can also be actually found out by electromagnetic waves. So these are few applications which actually motivates us to learn more and more about electromagnetic waves. Now when we talk about electromagnetism, it's a combination of two words, right? So it is electro plus magnetism. So what does it mean? It means that there is application of both electric and magnetic field. Later on, we also know that it has got some connection with optics as well. So it's a connection of both electric and magnetic field. Now what exactly happens here? Let's not go into the detail, but just a brief about this. These electric and the magnetic fields are actually coupled with each other, and they move in a direction which is actually perpendicular to each other, right? So suppose this is my electric field, and if I want to show the magnetic field, suppose this is my magnetic field. So both this electric and magnetic field are actually perpendicular to each other. So this is my electric field, in a perpendicular direction I get my magnetic field. So these are actually perpendicular to each other and they are coupled. So we call it as the coupled waves, right? So both electric and magnetic field are traveling together in the same direction but perpendicular to each other, and it is basically varying with time. So that is very important, varying with time. We'll come to know about that later. Now let's talk about what do you mean by Maxwell's laws of electromagnetism before we go to Maxwell's proposal, laws of electromagnetism. Now when we talk about laws of electromagnetism, there are basically four laws. Four laws. The first law is very important. You must have heard about this in your earlier classes. It's E dot ds is equal to Q divided by epsilon naught. Now this is nothing but Gauss's law in electromagnetism, right? The next law is B dot ds is equal to 0. This is also the Gauss's law, but this is in magnetostatics. So we call it as magnetostatics. The third law of electromagnetism is integration of E dot dl, thus the line integral, is equal to minus of d phi of p dt. This is nothing but Faraday's law, or it is more popularly known as Faraday-Lenz law. This is the laws of electromagnetic induction. And the fourth and the final law is B dot dl is equal to mu naught into I. This is Ampere's circuital law. This is Ampere's law. So these four are actually the laws of electromagnetism. But question arises that what Maxwell has done so that for which the laws actually gets changed. Now Maxwell has seen that these three laws, these were okay, but the fourth law, there were some doubts in the fourth law, that is the Ampere's circuital law, and based on that doubt actually he has modified that, and then finally we come to the Maxwell's law of electromagnetism. Now before we go to the correction of the fourth law and what are the drawbacks, let's just try to understand that what was Maxwell's proposal in connection with the fourth law. Okay, so before we go to that, let's see what was Maxwell's proposal. Now what Maxwell proposed, Maxwell said that from the third law we can see that if we consider the third law, we can see that because of the time varying magnetic field, we have got an electric field, right? The generation of electric field. So we have got a time varying magnetic field, varies with time. We have got the generation of electric field. So that was true, that was proved by Faraday. But Maxwell proposed that if I have a time varying electric field, will it generate a magnetic field? Right? So that was his proposal. So just to do a bit of more of that, time varying magnetic field produces an electric field. How can we prove that? Or we know that suppose we consider a magnet, got a north pole and a south pole, and then we have got these lines of force. And suppose I have got a loop, right? A conducting wire, suppose I have got a loop, and I have connected, say, an emitter here. I've connected an emitter here. Now if this magnet moves to and fro, I'll see a deflection of the emitter. What does it mean? That there is some electric field which has been generated, right? So because of this time varying magnetic field which varies with time, as I move it to and fro, I have got the generation of electric field and I should get a deflection in the emitter. So what now I want to know that what happens when there is a time varying electric field, will there be generation of magnetic field? So next we come to the modification of Ampere's law. Now what is the drawback of Ampere's law? Now Ampere's law, when we talk about, let's just start from the beginning. Now what is the modification of Ampere's law? Now why it is inconsistent? We call it as inconsistent, right? Now why it is inconsistent? Now let's suppose I have got a current carrying wire. Suppose it carries a current I, and then it's connected with a capacitor, right? So this is positive, this is negative, right? So I've got a current here. Now let me take a loop outside this capacitor, Amperian loop we can call it, as we know from the concept of Ampere's law that there is some Amperian loop, and irrespective of where the loop is taken, the current, there should be some magnetic field which is generated because of this current, right? So this is the first case. So in the first case what I have is nothing but, let me consider Ampere's law, it's B dot TL is equal to mu naught I. Now I say that what is my dot dl, integration of dl, okay, b I can take it out and that's a dot product, right? So dl, now dl means it's the entire length, right? So since this is in the circular shape of radius r, the length will be nothing but the circumference, which is nothing but 2 pi of r is equal to mu naught into I, right? So finally I get a magnetic field which is mu naught I by twice pi of r. Now let's take one more case. Let's consider the same thing here, but this time let the Amperian loop be on the surface of the positive of the electrode, the capacitor plate. Let this be the Amperian loop. Now what happens in the second case? I have integration of B dot dl is equal to mu naught I. Suppose I don't know the radius of that since it's on the surface. So let this side remain as B dot dl and is equal to, now what will be the current? Now the current within the capacitor is 0, right? The current within the capacitor is 0, the current flows outside the capacitor. So this we call it as the conduction current, right? Conduction current. So this can be written as IC. So I have got IC here, IC which is nothing but the conduction current. So this is nothing but 0. So what does it imply? It implies that P is equal to 0. Okay. So what he did, he took one more example. Let's take one more example. Again, let me take the capacitor. And now let me consider the loop within the capacitor. Similar case, here also I'll have V dot TL is equal to again 0 because it doesn't exist, and so I've got the magnetic field as 0. So I've got three cases. In the first case it's this, second case it's 0, third case is 0. But according to Ampere's law, the Amperian loop anywhere should give me a magnetic field. But the second and the third case are not giving me a magnetic field, it's actually giving me the magnetic field as 0. So obviously there is some contradiction, and that means that there is some defect in the law, and that I need to prove. Right? So next I want to say that it a circuit which is actually considered, it has got some inconsistencies, and now I want to know that what exactly happens and how do I prove that. So what I do, in the first case I was there, in the second case, let me take a small IC rather, IC was 0, in the third case IC is again 0, right? So I want to say that what happens exactly. So let me just consider one more time this figure. Now there is a current outside, but what happens inside? Inside there is nothing but the electric field. So there is some electric field which goes from positive to negative. That we know from our earlier concepts. So what is the magnitude of the electric field between the plates? So let's see, magnitude of electric field, that would be between the plates, right? So it is nothing but, if I denote it by E, is nothing but V by D. I know V is the potential, and what is D? D is the distance between the plates, right? So E is equal to V by D. So I can say it is nothing but V divided by, now, sorry, how can I write V? V can be written as Q divided by C in terms of capacitance. Again, what can I say, write the capacitance of a parallel plate capacitor? It is nothing but C, is equal to A epsilon naught divided by D. I'm write it this way. So let me write it as Q divided by C into D. Again I can modify it and write it as A epsilon naught D into D. So I cancel out this, and then I have got nothing but Q divided by A epsilon naught. Now I have this relation for the magnetic field, magnitude of the electric field. Now what is the direction of this electric field? Is nothing but perpendicular to the plates or surface. So I've got the magnitude and I've got the direction of the electric field. Now what is E outside the plate? It is 0. And what is electric field inside the plates or within the plates? It is nothing but Q divided by A epsilon naught, right? This is outside and this is inside. Right? Now E is not, now I want to find out the electric flux. So suppose I want to know the electric flux. So electric flux will be through the surface, so that is given by, how can we know the electric flux? It is basically denoted by phi, that can be given by electric field multiplied by the area, right? So what is my electric field? It is nothing but Q divided by A epsilon naught into A. So this A gets cancelled, so you have got Q divided by epsilon naught, so that is the electric flux. Now what happens if Q changes with time? I have got this very basic thing, Q, right? dq dt, if changes with time, I get the current. Now I'm interested in current, right? I am talking about current here, not the charge. So if Q changes with time, so there is a time varying charge, time varying charge. So if Q changes with time, I have got something as a current, and that is nothing but d of Q by d of t, dq dt. Right? So what can I write here? I've got this phi, so now if I write d phi dt, right, d phi dt is equal to 1 by epsilon naught into d, what would be that? dq d of t, right? So this dq dt is nothing but the current. So what can I say? I can also write it in this way, dq dt is equal to epsilon naught into d phi dt, right? So if I write it this way, this particular thing, so let me just mark it as a very important expression. So this particular thing is something which we call it as the displacement current. This is the displacement current, and this is given by epsilon naught into d phi dt. So this is the expression for the displacement current. Now let's go back to the Ampere's law. Ampere's law. Now if you go to the Ampere's law, it's nothing but integration of B dot dl is equal to mu naught into I, or right side IC. Now let's just do a modification. So we have got a conduction current plus a displacement current, right? Now if I have got a conduction current and a displacement current, what can I write it? I can write it as mu naught into IC plus mu naught into I of t. Now what was my displacement current which I just found out? It is nothing but mu naught into epsilon naught d phi b, let's write it as d phi b, that is the magnetic flux. So this is my final expression. So that means that the modified equation is nothing but Maxwell Ampere's law, and this is written as integration of P dot dl is equal to mu naught IC plus mu naught epsilon naught d phi b dt. So this is my Ampere's Maxwell's law. Very important. So Ampere's Maxwell law, that is the modified law. So I have got the four expressions. Let's just go back. So I've got the four expressions. So here this particular thing gets modified, and then we have got plus mu naught epsilon naught d phi b dt, right? So we have seen that the Ampere's Maxwell's law is actually getting modified here, and that is nothing but Ampere's Maxwell's equation. So the four laws of electromagnetism with a modified Ampere's law is what we call as the laws of electromagnetism. So some of the terms that we get here are epsilon naught and mu naught. Now, epsilon naught is actually the permittivity, and mu naught is permeability, and it is related with the velocity or the speed of light as 1 divided by root over epsilon naught mu naught. So we can see that C is something which is related with optics, right? So we can see that this is also related with optics. As I said before, electric field plus magnetic field plus optics are all actually interrelated. So whatever I've done till now, it's actually the integral or integral form of Maxwell's equation. Now let's just talk about the differential form of Maxwell's equation. Now what are the differential form of Maxwell equation? Now differential form of Maxwell's equation, it's a bit different, and from for knowing that we need to know what is the concept of divergence, curl and all. So let's just write the differential form first. So the best way to remember the differential form is write it in this way: del dot E. The laws are the same, the Gauss's law and Faraday's law and Ampere's law. Del dot B, again del cross E, sorry, and then finally del cross B. Now these are the four equations. Now first one is rho divided by epsilon naught. Second one is 0. It is minus del B del T, and then we have got, it is nothing but mu naught into J, right? So again, Gauss's law in electromagnetism, Gauss's law in magnetostatics. Again, this is the Faraday's law, and then we have got the Ampere's law. Keep in mind again that these are not the Maxwell's equation, these are the laws of electromagnetism in the differential form. Again, first three laws were okay. And the fourth law is obviously having some doubts in it. Now, how do you know that what are the doubts present here? So before we proceed further, I want to know about delta. I want to know about delta. That what is exactly delta? Now you see, we'll be going to the concept of divergence, something we call it as gradient and curl. Now, what is delta? Delta is nothing but an operator. I know you should know about these things, but still, I have got a 2 or a 2 and then I have got 4. Does it mean anything? No, right? I need to put some symbols here. So it is plus and equal to. So this equal to and plus are nothing but operators. So this is nothing but an operator similar to that. But a 2 alone is meaningless. Operator alone is meaningless. I need to put some numerical with that. So obviously a delta operator should have some values with it. So let's take the simplest example. Let's take a vector, say R. How can we write R? R can be written as I cap x plus j cap y plus k cap z. So I have got this. Now I want to find out the gradient, divergence and curl. So if I want to find out the gradient, it is nothing but the multiplication of the operator and the vector. So what is my delta operator? Now it's important. Delta operator is nothing but I delta delta x plus j del del y plus k cap del del z. So this is the operator or the delta operator rather. So when I multiply it, what can I say? I can write it as I del del x plus j del del y plus k del del z into I cap x plus j cap y plus k cap z. So I have this. Now if I want to just change it, what can I say? Let's say that now if I know from vectors I dot I is equal to 1 and I dot j is equal to I dot k is nothing but 0. So let's see the first term I dot I. So I've got a 1 here. Then del del x of x, again it's 1, right? Plus then I dot j, it would be 0. Then again I dot k, it would be again 0. Similarly with other terms, we'll be getting this one term. So this j dot I would be 0. And then j dot j would be 1 dot del del y of y is 1 plus again 0 then plus 0 plus 0 plus 1 dot 1. So finally we get the relation as nothing but 3. So this is my answer and this is nothing but the gradient. Now suppose I want to find out what is the curl or divergence. Right? The divergence, when I talk about divergence is the dot product. Divergence is the dot product. So how do I find out divergence? So how do I find out divergence? Divergence is the dot product. Now for this vector it's the same result. But for some other vector it might be something different. So it's just the simplest example I'm taking, del del x plus j cap del del y plus k cap del del z dot of I cap x plus j cap y plus k cap z. So the answer would be again 1 plus 1 plus 1, which is nothing but 3. Now, before we go further, what is the importance of gradient and divergence? Now, gradient, see, it has got the variation with respect to x, y, and z. So, in which direction the vector is having the maximum value, that is actually given by gradient. But what does divergence give me? Now, divergence has got a meaning which is quite physical. See, suppose I have got some lines of force. And let me take this much area. Now, how many lines of force are crossing this area? So, it's 3. So this is just an example. So I'll take just a further region and then I'll say in the same area and then the number of lines of force are crossing is just 1, right? So as I go further and further from the originating vector or the point from where the vectors originated, I'm getting the number of lines of force as decreasing. So that means that obviously there is some divergence in the lines of force. So these sort of ideas are actually given by divergence. Next, talk about curl. The curl is nothing but the cross product of the vector with the operator. Now the best way to find out curl is in the determinant form. So I can write I cap, j cap and k cap. Now these are common, right? The vectors which are common between delta and r is I, j and k. and then I can, since I have got delta first, so I'll be taking the coefficient of I, j and k in delta, del del x, del del y, del del z. And the coefficient of I, j and k in R is nothing but x, y and z. So I'll be just doing it for I, j and k can be found out easily. So if I do it for I, how do I find out? Just cancel this and then cancel this, and then I have got I, and then I can say this is nothing but del del y of z minus del del z of y, correct? Suppose then I've got plus j, so if it's j, then I can take it is nothing but, that is normal matrix, del del x minus del del x of z plus k cap, and then I've got del del x of y minus del del z of x. Now I can say that del del y of z, what is this? Nothing but 0. This is again 0. These things are also 0. So ultimately the result is 0. So the curl is 0. So this is the curl. Now what does curl signify? Now suppose I have got water ripples. These are water ripples, right? Now at any point I want to find out the direction of the vector. What would be the direction? That would be nothing but a tangential point. A tangential point, right? So if you consider a set of these vectors would be in the circular path. So this idea is actually given by something which we call as curl. Okay. Now, what does it mean when the divergence and the curl is 0? Suppose I have got a divergence of R is 0. This got a technical term attached to it, and we will call it as solenoidal. Again, suppose the curl of R is equal to 0, then we call it as irrotational. Okay, so these are the technical terms I need to know. If divergence is 0, that's solenoidal. That means R is solenoidal. Okay, and if the curl is 0, that means the R is nothing but irrotation. Now, since I've learned about divergence, curl, and gradient, how can I apply for the modification of the Ampere's law? Okay, we'll be studying about that now. Let's not talk about the other laws. Let's just talk about Ampere's law. Now, what is Ampere's law in the differential form? Differential form, it's nothing but del cross B is equal to mu naught J. J is the current density. Okay. So, if I have del cross B is equal to mu naught J, so let me take divergence on both sides for this. Divergence on both sides for this equation. Now, if I take divergence on both sides, that means I'll take delta dot delta cross B. That means delta dot mu naught into J, right? But from vectors we know that the divergence of a curl is always 0. So what I have here, I have delta dot mu naught J bar is equal to nothing but 0, right? Or mu naught is a constant. So if I divide it throughout by mu naught, then I can have delta bar dot J bar is equal to 0. So this is my result from this particular thing, right? But I have got an equation which is called the equation of continuity, and which is actually proved. And what does the equation of continuity tell me? It tells me that divergence of J bar plus del rho del T is nothing but 0, right? So it means that del bar dot J bar is equal to minus del rho by del T. So you can see there is a contradiction, right? This is nothing but the charge density. So rho is the charge density. So we what is the contradiction here? That del bar dot J bar, if I take divergence of both sides, comes out to be 0. But actually del bar and J bar cannot be 0. It's actually minus del rho del T. So it should have some value. So obviously this result is wrong because this experiment is proved, right? So this is proved. So this is wrong. So what does it mean? That there should be some modification in this law. So in this way we can say that Ampere's law is actually not correct as found out by Maxwell. This is a bit different and more mathematical when we consider the integral form. Now let's see how do we correct this. So similar to earlier pattern, what we can say? We can say that let's just take one more quantity, suppose JD, add JD to it. Okay. Now let's take divergence on both sides. What happens if I take divergence on both sides? I'll have del bar dot del bar cross P bar is equal to, let's mu naught is a constant, let's take it out, del bar dot J bar plus JD bar. So this side is 0, this side is 0. So dividing it throughout by mu naught, so I can have del bar dot J bar plus del bar dot JD bar is equal to 0. So what is my del bar dot JD bar? Is nothing but minus of del bar dot J bar. But what is del bar dot J bar? It is minus del rho del T. So I can write it as minus minus gets cancelled, so it is del rho del T. Correct? And one more thing we need to know, that this rho is actually a function of the electric field. It is written as the d bar. Please remember, d is nothing but epsilon naught E. Okay, so rho is del bar dot E bar. So what we can say, we can just modify that a bit more. Del bar dot J d bar is equal to del T of del bar dot d bar. So since delta is an operator, we can take it out and we have got del d del T. So what does it imply? It implies that JD, if considered one more quantity, JD, that is nothing but del of T. Correct? So what are the things we have found out? We have found out that JD is equal to del of del T. So what was the Ampere's law? We have written the modified one. It is nothing but del bar cross P bar is equal to mu naught of J plus JD. So we can write it as mu naught J plus mu naught into del D del T. So I can also write it as mu naught J plus mu naught epsilon naught del E del T. Please remember, D is equal to epsilon naught E and B is equal to mu naught H. So what are the four Maxwell's equation? Again, it's important. So just revise. Del dot E is equal to rho by epsilon naught. Number 2, del dot P is equal to 0. Number 3, del cross E is equal to minus del B del T. Faraday's law of electromagnetic induction. And number 4, del cross B is equal to mu naught J, what we have written above, plus mu naught epsilon naught del E del T. Please don't make any confusion between B and H. B is equal to mu naught H. So if you write it in terms of H, it would be nothing but divided throughout by mu naught. So divided by mu naught. So if I divide it by mu naught, this would be just J and this would be just epsilon naught del E del T. So the final expression I will have is nothing but del cross H is equal to J plus epsilon naught del E del T. So it's always better to remember in terms of B and E, and then you can easily replace it with D is equal to epsilon naught T and B is equal to mu naught H. And that also is existent, the value of C is nothing but 1 divided by root over mu naught epsilon naught. So these are the two things. One is the integral form and the second one is the differential form. So we have written the laws of electromagnetism in integral and the differential form, and then finally found out the drawbacks, and then the Maxwell have corrected that using the concept of divergence, and in the other where we use a capacitor in it. Okay. So with that we end today's class. Thank you.